Hi, at-home students. Just want to say hello for me. Every so often, just want to show my face. And then also just want to give you a line, ask you how you guys are doing, and give me a call, give me an email back to see, tell me how you're doing. Anyways, we're going to start class in just a bit. Happy Monday. Super happy Monday. I can feel the vibe. That's the vibe. Yeah, that's about right. Great, I got it right. Grades are due for the third time. Grades are due Wednesday. I did update grades yesterday, so whatever is in Google Classroom should be current as of this morning. So if you're missing something, turn it in. If you're not missing anything, you're doing great.
Do you have the setting on where we can go to like, it's like view your work and then you can click on it and see like your percentage in the class?
Should be.
Okay, because it was on last semester and I checked and it wasn't on this semester. But I don't know if that's just like.
I will check on that.
Okay.
All right.
It's just always nice to see the percentage so we can adjust it if we need.
Yeah, I thought that was the whole point of grade book online.
Yep.
Oh, you guys, and then I'll check it after calculus class, but you email me if you still don't see it. That's the whole point here. All right, let's jam. So we've got equations here. One more little thing we got to do. Actually, two more things. No, one more thing we got to do. This is the end of it as we turn to something called the parametric equation here. So, well, it's called multiple angles. We've kind of done it before already, except we're going to see it in a different light. How about if you can't get rid of that multiple angle? Remember, we have double angle formulas, right? So we can maybe use those, but if you can't use that, you're stuck. So that's where we're at next here. So involving multiple angles, 6.3. Boom. We'll skip that one. Let's jam to the other one. I guess we should go back here. So what are we gonna do real quick here? Number one, simple one, just to get us started. Second, having to use identities. Hey, this looks familiar. Having to use the quadratic formula, and eventually a real life problem. So let's jam. All yours for this one. We had something similar to this in 6.1, but it was equal to 0. And that was easy to do because you could take sine 2 theta and you could use an identity. This one, you can't use that same identity because you're stuck seeing it as sine 2 theta is equal to -3 square root over 2. That's right. My stuff together. All right. So real quick here, let me show you the wrong way first. Good. If you were to change this into 2 sine theta cosine theta, is this helping any? If it was set equal to 0, it would help because then we can simplify those out, right? Because it'd be a factoring technique at this point here, but it's not set equal to 0. Okay, so we have to figure out a different way to do this. And so my way is a little different than the textbook here. And so I'll show you my way because I like my way. That's the whole point of it being my way. So 2 theta, notice we're trying to figure out what 2 theta is, but our domain is in terms of theta. So here's what I'm going to do. I'm going to go ahead and just multiply everything here by 2. That means 0 times 2 is still 0. This becomes 2 theta. And this becomes 720.
Could you not divide by 2?
I'm going to multiply by 2 first, and then I'm going to divide out by 2. Because eventually, at the end, I still want theta to be between 0 and 360, right? But just for the purpose of finding my angles, I take this and you could also think of it as doing 2 revolutions if you like. Cool, okay, so here's what we're gonna do. I need to figure out, oh, hold on, my trig function is already set to something, right? So let's go back to my unit circle, and I'm gonna go like this, and I need to find when is sine negative √3/2. Matthias with the textbook, awesome. Let's see, no, let's go backwards here. So Grant, which quadrant should I be in? Awesome. That's cool. And I like to sort of think about this here. If it was a 1/2, I would be like right here because I'm going down along the y-axis, right? If it's a √3/2, that means I'll be all the way down here. Boom. And Matthias, all yours. Give me the angle measurement that makes that happen. 240 with the smaller circle on top of the extra 0.
You're really smart.
Adrian, the next one. This one right over here. Oh, went too far.
It appears to be 3, 0, 0, but a smaller 0.
Awesome. Okay. I like the smaller 0.
It is happening right now.
So 420 and 300, that's cool. So what we want to do is we want to go all the way to 720, so, or 2 revolutions. So Zachariah, all yours. I found 240. What am I going to do here in order to get to? Oh, sorry, hold on. Sorry, guys. You can say this, right? I found this right here. True. It's 2 thetas equal to 240. It's also equal to 300. And anybody from the audience here. If I go another revolution, what am I going to get? Or Zechariah, whoever's first. 600? Cool, I think so. Let's see, we're going to go this way, right? And then we're going to go 1 full revolution. How about 600, right? To get another revolution, we're going to add 360. And 660. So let's go over here. Let's see, this is going to be 600. Notice it's not just doubling of things, right? And I got 660. Easy stuff. I still want to solve for theta though. So here's what we're going to do. We are going to just divide everything by 2 all the way through. And question, are all my angle values now between 0 and 360? I think so. Let's see, that's going to be 120. That's going to be 150. I have 300 on my hands. And 330. Are we good? Cool. 2 things happening this Friday. Something, a deadline for something or no? Deadline for something school related or no? This Friday.
Matthias Day is this Friday.
Oh yeah, that too. That's right.
I don't think we have any. We have a history outline due on Wednesday.
Gotcha. Okay.
And then we have to start writing in our rector.
Oh my gosh, we have anatomy test.
When?
That's what we have. Tuesday, next Tuesday.
What? Oh, God.
Yeah, sorry.
Just to scare you a little bit here. Okay.
I don't. I mean, then I probably wouldn't have to take the anatomy.
I mean, at least I think we do. That's what she said to me.
I don't know what the road we are, but I
She was
wish I
like,
did.
we'll have one, we were supposed to have one on Tuesday, but we'll have one from Tuesday. And I was like,
Okay. If you say so.
This is the funniest.
All right, we go with number 1. Yeah, and now we're between 0 and 360, right? Just by dividing that 2, dividing by 2, and we got all the values we need. Okay, a little bit more complicated, not by much. How about cotangent? 3 theta Let's go in terms of radian measurement. Let's change that up. And this one, since I already have a trig function that's equal to something, I might as well think about it as, when is cotangent 1? Cotangent is 45 degrees. Let's do this first here. Let's see. Think of 3 theta or 3 revolutions in your mind if you like, or if you need to, you can think of it as going all the way out to 6 pi. We're good. 3 revolutions or 6 pi, whichever way you want to think about it. And since this is all set to go, cotangent is the reciprocal of tangent. But that 1 is kind of like the, because reciprocal of 1 is still 1. So technically it's whenever cotangent is 1 or tangent is 1, whichever. Grant said 45 degrees. I agree. Or what's the radian measurement? 45 pi over 4. Okay, and then another time that happens.
Oh, is it quadrant 3?
I think it is, yeah, quadrant 3, that's when both of them are negative. You know, that guy. 5 by 4, perfecto, I go with that. And we keep on going, is that right? So now the question is, what's the next one in quadrant 1?
Is it 9?
Cool, yeah. The best way to do it, since we're in denominators of 4, you might as well think of 2 pi in terms of 8 pi over 4.
Yeah, let's go.
We both,
So-
took like a minute to think about it, and then we're saying,
9 pi over 4. Next one. Then we think about how much we add to get to the next one, right? We are a pi over 4, we got to 5 pi over 4, but adding a 4 pi over 4. So this little connection right here is just an addition of pi or 4 pi over 4 each time.
So it's 13 pi over 4?
Sounds good. All right, the other way to think about it is, notice we're exactly half of a circle apart, so technically we could have just added 4 pi over 4 to get to 9 pi over 4, right? It just comes cyclically all the way around. 30 pi over 4, add another. What's 7? You guys see if you, is that right? 17 pi over 4? We're going 3 times around. And another 4 pi over 4. Whew, okay, I'll go with 21 pi over 4. And these, unlike the degrees, you may want to write separate. So I'm going to write it like this. I'm going to say 3 theta is equal to pi over 4, comma. 3 theta is equal to, 5 pi over 4. I don't know, why do we do it differently? A lot of work here.
Is there any point where you can just stop, and know that when you divide by 3, it won't be within the 2 pi range anymore? Or will it all end up being within the 2 pi range?
It should.
But you can do it 3 times, and then everything will be within the range.
Ooh,
Right, like we did it up to the values that will be within 2 pi.
except we have to add it in as opposed to multiply it in, right? As long as we know that. Right, because we're adding 4 pi over 4 each time, as opposed to just doubling the angle or something.
Right, but at the end, because like in the first one, we divided everything by 2 at the end and said, oh, look, everything is between 360.
Oh, gotcha. Yeah, sorry. This is what I'm thinking. Yeah, you guys did, so 4 pi over 4, right? Is equal to this, right? So if you were divide by 3, gets you pi over 12, right? Yeah. That would work as long as you're sort of seeing this very easily in your mind right
Okay,
here.
so we do just have to go all the way to 6 pi?
Mm-hmm.
Yikes.
Or 3 revolutions, right? Because if you got 3 revolutions down, you're good. And we did already 3 revolutions here. So the little pattern that you guys can see maybe is like this right here. After you put it down, 3 pi is 13.
Well, then isn't every denominator just gonna be 12?
Correcto.
Oh, unless you can simplify.
Yeah.
George, I think this is what you're getting at, right?
Yeah.
If you are dividing by 3, same thing as multiplying by 1/3. So eventually theta becomes pi over 12. So if you can kind of see the pattern already, then you don't have to put down all of them. If you do need to write down all of them just to sort of do the math next to it. And I don't know, in algebra, did you guys ever do this here? You divided by 3 on one side, but you multiplied by 1/3 on the other. Have you ever done that? I don't think we ever do that because algebra doesn't have denominators already placed. So this would be 5 pi over 12. And jamming. Oh, this one, notice right over here, can't do that all the time because that little 9 pi is going to reduce, unless you could do it in your head. So this would reduce down to, let's see, that becomes a 1, that becomes a 3. So this is a 3 pi over 4 still. We're good there. So not all of them are just going to have denominators of 12. (13 pi over 12). And then 17 pi over 12. Are we good there still? And then this would be off to the side. This would be 21 pi over 12 reduced down to, let's see, by 3. 7 pi over 12. Hold on, 7 pi over 12. Is that less than 2 pi now? Yes, right. So we go back to our original, we were able to get into our original domain restriction here. Cool. All right. Let's jam. Number 3. Are we good there with number 2? Some people are just gathering it by osmosis. It's so cool. Like, wow. I mean, I never thought that math could be gathered by osmosis, but I guess chemistry and math do go together. For some. That's cool. Okay. Getting a little tiny bit more complicated, I think. Yeah, there, yeah, it's still the same, yeah. Boom. Maybe you might have to use an identity. I'm just thinking maybe. So all yours here. Find all solutions to that equation. Whoa. If x is measured in radians from 0 to 2 pi, so same restrictions as the previous problem, just written out. The first two as. I think that's where the angle is in the book. Anybody know this cosine of 2x, cosine of x plus sine 2x, sine of x? What is that formula? And what is the simplified version of that? Cosine, cosine, sine, sine. No. Sorry, class. 1 second here. I did make the mistake. Can we chop this off right here? Put a little minus sign instead of plus? I'll make things so much better. Boom. So either textbook or back in your notes somewhere or from memory. Cosine, cosine minus sine, sine.
So this time you would want to change it into the sine 2x is like the 2 sine x cosine x, or
Ah, okay. So real quick here. So you're thinking double angle formula for cosine?
yeah, that one was actually sine, but yeah. Is
That would complicate things even worse.
okay.
That means you would have
It's not one.
two terms.
No, no, that's cosine.
Mm-hmm. So some cosine of something times cosine of something minus sine of something, sine of something. I don't know. It's somewhere there.
Oh, it's cosine A plus.
Oh, cool. Yeah, this right here is just the addition formula. So let's see, cosine of A plus B is equal to cosine of A, cosine of B minus sine of A, sine B. That little formula right there. Because notice whenever we do this here, what's going to happen is it's going to be cosine of 2x plus x. Voila, love it. That makes it so much easier. Then I just have cosine of 3x is equal to 1 over root 2. And I'm going to give you guys about 2 minutes to try it yourself. Can you guys finish it off? Cosine of 3x is equal to 1 over root 2. Three revolutions again. And I'm thinking right over here on my unit circle. Can't be a unit circle if the lines don't connect to each other. So let me draw the unit circle again. Much better. Let's see. 1 over root 2. It's cosine, so it has to be in quadrant 1. Quadrant 4. All right, and look at previous example here, just sort of see how you do the rest of the math here. And let's see if we can just line them up. I guess it would be easy just to line them up, and let's see if we divide by 3. So first one is, isn't this the same thing? This is the same thing as root 2 over 2. In fact, on your textbook, I think it has 1 over root 2, right? Boom.
In the book, it's 1 over radical 2, but it is that way in Slater most of the time. And
Root 2 over 2 in Slater, or 1 over root 2?
the
Slater is root 2 over 2, and the back of the book is usually 1 over.
Gotcha. Okay. Cool.
The back of the book is stupid.
I'm not sure it has an IQ setting in the back of the book. Adrian, what do you say? What's the degree measurement in radians?
Oh my gosh, it's right. No.
No.
I literally
Love it when that happens.
Alright.
Yeah, it's pi over 4.
Perfect. Pi over 4, 7 pi over 4, and then now, in fact, even talk to me here. Would it be easier to add right over here? Add a, because last time we were adding 4 pi over 4 goes half a circle, right? But it's almost easier just to add 8 pi over 4 to the one that you already know, as opposed to flipping back and forth, up and down. Because you're adding 2 pi essentially, right? So pi over 4 plus 8 pi over 4, 9 pi over 4, plus another 8 pi over 4. Are we okay with 17 pi over 4? Turn back around. Let's see, let's add 8 pi over 4 here. Another 8 pi over 4 there. Let's see what we get. I got, let's see, 15 pi over 4, and check me just to make sure I'm doing it correctly here. I got a 23 pi over 4. Everybody good there? Okay. Do we need to list them out or no? I guess I'll list them out. Let's see if I can do it the shorthand way. So 3x is what I found is pi over 4. 9 pi over 4. Doesn't really matter what order it comes in. So when you look in the back of the book and your order is different than what it says there, that's okay as long as you have all of them there. A lot of mental math over here. Okay, let's divide this guy by 3. Each time we divide by 3, we're going to check to see if we can reduce stuff. So this is just pi over 12. Reducing this guy. So that's pi over 12. Yep, boom. How about this? We'll go with answers for each one of these here. Are we okay with 3 pi over 4 for the second one? That's cool. Next one will just be 17 pi over 12. 7 pi over 12.
5 pi over 4.
Thank you. And 23 pi over 12. Done. Are we good? Essentially, if you guys remember in algebra class, you guys did like polynomials, right? And you learned how to add, subtract, multiply, divide them. Then you learn how to graph them, and then you learn how to solve them. Essentially, that's kind of what algebra is all about. We do that with linear functions. You learn how to solve for x a way long time ago. You learn how to graph them. Right? Actually, you learn how to simplify them first. You learn how to solve them and graph them. All right, cool. From then on, you went polynomials. From then on, you went rational functions. You guys remember those fractions with x's inside them? Whew. You learn how to simplify them. You learn how to solve them and graph them. That's essentially, and then radical functions did the same. So trig functions, we do the same. We learn how to simplify them. We learn how to graph them first. Now we learn how to solve them. Okay, Jim, and I think we are good there. Okay. It's stuck. It's stuck, but that's okay. I have the power. Boom, okay. All right, yeah, I am trying to scare you with the 8 over there. Absolutely trying to scare you. But that's the fun part about teaching. So here, what I want is all the degree values in the whole entire world. Forwards, backwards, and
Oh, you should get 1/2 on the other side.
That's
by
cool.
2, so that you have
Oh,
cosine
it's
16.
easier, isn't it? You don't even have to write them all out.
I think I agree with Grant there. Matthias, Matthias, what am I gonna do?
And I was like, oh, it's easier. You just need special K.
Mm-hmm.
Special K.
Special K. I like
I
that
just
special
want the
K.
biggest possible thing that it was.
Everyone gets me that. It's like, here you go, ha ha ha. And I'm like, okay, people, it's not that funny anymore.
8 theta. That's gonna be a lot of writing out. Forever, is that right? Because it's all the degree values.
Yeah, it would be a lot of writing out no matter what. Psych, you'll be here for the rest of your life.
When I was teaching one time in high school,
Birds are back.
No.
That would be a class. Here's your math problem. You'll be doing it for the rest of your life.
I was teaching high school. It was Algebra 1 class. And just for the fun of it, I told the students, you know what? I want a board that goes from 1 to 1 million. And if you can do that for me, I'll give you the A in the semester. Because I would just love to have a board like that. And we're talking about the fact that you can't get to some places, right? And then I did it in class. And we did the proportions to it and all that stuff. So it takes you, if you can write, is it per second or every 2 seconds? It should take you about 3 years to write it from 0 to 1. And so we did the work there and everything was fine and everything was cool. Then we go home, come back the next day. And the kid got up to like 4,000. He was jamming and he was serious. I was like, whoa, dude, stop. No, don't do that.
Did you give him an A?
And no.
Good effort, but
It's
not.
like you walk into the class, and he's like on the floor. His
I'm going. Anyways, yeah, that's if you want to list all of them, Georgia. It'll be here quite a while.
You're just like, I'm good.
Georgia figured that one out already.
Promise me an A. Yeah.
She's just spinning around the unit circle.
There's a cosine is equal to 1/2. Let's see, cosine equal to 1/2. That's going to be in quadrant 1. That's going to be this one.
Yeah. Looks like a ray off of the
I think it's pi over 3. Is that right? Oh, that's right. Yeah, that is 60 degrees. Boom, and then I'm going to go down here as well.
So, in like application problems, how often are the angles actually equal to 1/2 square root of 3 over 2 square root of 2 over 2, 1 or 0? Often or
we'll-
not often?
What if he just gave you like 2
No, usually it's in calculator mode and we get to them.
Okay.
So we'll get to those today, hopefully. Okay, 60 and 300, is that right? Everybody agreed there? Okay, the cool thing is we just write the K value next to them. So the answers are 8 theta, because right, we still have a multiple angle in our hands, right? It's 60 degrees plus 360 degrees K. That's one answer, 1 unit circle. And then 8 theta is equal to 300 degrees plus 360 degrees K. And we'll define K in just a bit here. Boom. Okay, so if I'm going to use solve for theta only, I think I'm going to have to do that. Ooh, 60 divided by 8. I don't think that's going to come out nice, but let's see. Is it a decimal answer? Can you guys give me a decimal answer of that? Six, 4, almost like thinking 7.5 or something, right? Because that's going to be 7 times 8 is 54. Oh, cool. 7.5 degrees plus, and then I need 360 at 8. 45. Perfecto. Okay. Are we good there? Just listed all of them for that first angle. And
What
then
if would you have checked all 2 million or whatever of his answers? What if he just came in with like 2 million numbers?
Oh yeah, that's true.
And like told you he wrote an algorithm to calculate it, would you have checked them?
every single integer from
What if he solved it using a computer and he actually did it?
Grant, the more you talk, the less likely he is to let us do it.
I mean, I don't.
Are any of us gonna write a computer program?
No, but we could
It
have
would
used
be
those
really
shortcuts.
That's true. It would be really funny.
Yeah, I think
Grant,
we
I
should
would
do
have
it for purely comedic
So
value.
37.5.
37.5 and 45 degrees still, right?
Yeah.
And then I can define K. K is an integer. Hey, that was actually easier than the other ones, wasn't it? Just because we have that K value helps us out. I like, in this case, yes. Okay, let's see what time we have here. Still jamming. Just want to get to the the calculator one here, just a bit here. Okay. Next is, of course, the factoring problem. So get it more complicated here. 2 sine squared of 3 theta plus 3 sine of 3 theta is equal to -1.
What was the last part of the last question? I didn't
Oh,
grab
sure. Dunk, dunk.
That's good, thank you.
Mhm. And all right, let's go a little bit faster just so we can get done on time with this one here. We'll get to the application question. We'll save that for Wednesday, but at least we'll be done with all the stuff. You guys should be able to start on the homework here. So I see sine squared over here. I also see a sine. I see the the degree 2 form of it, and also the linear form. In my mind, that means quadratic formula or factoring. So I'm going to bring the 1 over, set equal to 0, and it's factoring time. Or quadratic formula. Let's see. Maybe off to the side. We can even try this here. Can you think we can factor this down? Because it's going to be the same factoring. I'll let you guys do all your different ways you do factoring. How about that? See if it works out.
2x plus 1 times
No.
times x plus 1.
Yeah, 2 in front is a prime number, so it's only 2x times x is the only way you can do that. 1 is nice because it's the only way you can do it is 1 times 1. And then we check our middles. That's 2x plus another x makes 3x. Perfecto. Okay, so we didn't have to do quadratic formula. We're going to substitute 2 sine 3 theta plus 1 and sine 3 theta plus 1. Set each of them equal to 0. And let's go for it here. So let's see, I got sine of 3 theta is equal to -1/2, I assume there is good. Sine of 3 theta is equal to -1. Can you finish it off? Give you guys like a 20-second head start. -1/2. It's the sine value. So it has to be on the left side of the x-axis or the y-axis. And it's just a little tiny bit up. So it has to be this one and this one. It's the one that's just tiny up. Radian measurement, yeah. So this is has to be 5 pi over 6. This could have to be a 7 pi over 6. And that's done. Let's get back to this one here. This is going to be, oh yeah, that's nice. Sine is -1 only here. And then this is 3 pi over 2. Okay, based upon those 3 answers, can you write the rest of them? Let's see, 3 theta. Let me write it on the next slide because I need more room. I have, let's see if I can fit it. 3 theta is equal to 5 pi over 6 plus 2 pi k. Everybody agreed there? Some more mental math here. 3 theta is equal to 7 pi over 6 plus 2 pi k. And 3 theta is equal to 3 pi over 2 plus 2 pi k. All right, dividing by 3 means I'm going to divide by 3 here. Technically, I'm going to multiply by 1/3 here and then divide by 3 here. So that means that little top one now becomes theta is equal to 5 pi over 18 plus 2 pi thirds k. I'm going to run out of space here. At least want to do it on the same slide. Let's see, divide by 3, multiply by 1/3, divide by 3. So 7 pi over 18 plus 2 pi thirds k. I'm going to have to go backwards here. Theta is equal to this one right here. Oh, this one's kind of funny because the 3's are going to cancel. 3's cancel there. This just becomes pi over 2 plus 2 pi thirds k. And then I have to declare k is, it doesn't want to write anymore. Sorry, pass it's all backwards here. Hopefully you have more room on your sheet of paper. So that was my first one, second one, third one, and then I define my k value right there. K is an integer. Okay, think we can make it. One last problem here. And of course, we're going to round to the nearest 10th of the degree. Most likely we'll have to use a calculator. No, you have to use a calculator. So 2 sine theta 2 sine squared 4 theta minus 2 cosine of 4 theta is equal to 1. All right, I'm going to jam so we can finish in 5 minutes here. So I see a sine squared, I see a cosine. Anybody? What should we do? Perfecto, yep. The linear form here is cosine. So I'm going to change everything in terms of cosine. Multiply by 2. Let's see, now I at least have my cosine squared. Let's see, now I'm going to put cosine squared first. The cosine value second. I'm going to bring that little 2 from the beginning to the end there. Okay, and I'm going to go just a bit faster here. So let's see, then I have to subtract 1 from both sides. There's that right there. Let's see, I have negative 2 cosine squared 4 theta minus 2 cosine 4 theta. What is that, plus 1? You guys keep me honest here. We good? Make sure I do the calculations correctly here. Good morning, Ms. Rick. Multiply through by a negative 1 gets me a positive 2 cosine squared 4 theta plus 2 cosine 4 theta minus 1. Boom. Can't factor out a 2 out of here either, huh? Okay. If this was an even number over here, at least I could factor out a 2, but I can't. So again, off to the side if you need to. 2x squared plus 2x minus 1. Can we factor that down? Try a few things here. That's that and that, right? I don't think we can. If it was a 3x, it would have been fine. Or if it was a 1x, it would have been fine. But this does not work. What are we left with? A quadratic formula. Okay, let me rewrite this. 2 cosine squared theta, just for the torture of Grant. That's all this problem is for.
I agree.
You're a sadomasochist, so
He's a grant masochist. Yeah, he's a grant masochist.
I'm not, I don't. No, I'm not. I don't want to do quadratic. If I did, I would be happy to do quadratic formula.
All right, let's put this together slowly. Let's see. It's negative b plus or minus b squared minus 4ac divided by 2 times a. Whew. Okay. Let's see. That should give us 12 because it's 8 plus 4. Boom. Shorter here. 2√3. Okay, I'll go with that. Let's see, and then I'm going to reduce each of these guys by 2. So that's reduced by 2, that's reduced by 2, and that's reduced by 2, leaving us with a -1 plus or minus √3 over 2. Again, all the numbers are there. We deal with ones and twos and √3s, but not in an addition or subtraction sense. That's the problem. So I got 2 answers here. I got cosine of 4 theta is equal to -1 plus √3 over 2. And I have a cosine of 4 theta is equal to a -1 minus √3 over 2. We're good there. Okay, and so let's see if we can put this together. If it turns out to be a positive answer, that is fine and dandy. We're good. If it turns out to be a negative answer, we are going to have to change it to positive and think about a reference angle. So there's a little bit of work here involved. So real quick here on your calculator, can you give me what the value of this? What's -1 plus √3 and then divide by 2?
I got 0.36, no, well, 366, but 0.36.
Yeah, that's fine. All we care about whether it's a positive number. If it's a positive number, that's great. So here's, and we are running out of time. So we're gonna have to stop here right before the end. We good? So don't do the calculator questions on the homework yet, unless you want to figure out yourself just for the fun of it. I will finish it up on Wednesday. Last part of it here.
So we'll do homework questions on that.
Yes, And we'll finish up this section. We'll go and we'll maybe start the next one here. Just a little bit. Cool. Have a good rest of the day.
Thank you.
Huh?